Hi everyone, today we are going to present our numerical programming group project. My name is Betty Singh and here's are my team members Yang Yiqian, Muhammad Iqmal and Sabina. So first I would like to move to our introduction. This project aims to design a MATLAB Simulink programming for analyzing an ACRC electric circuit as shown in figure 1 below by using MATLAB Simulink software. With this, we can understand MATLAB Simulink programming technique and indirectly understand circuit analysis technique as well. Next, I'll move on to the problem statement. Firstly, how is the variations of input voltage amplitude influence the behavior of the capacitor output voltage? Secondly, how is the variation of input voltage frequencies influence the behavior of the capacitor output voltage? And lastly, is the given circuit is a low-pass filter? Next, I'll move on to the objective. So first, we aim to examine how the variation of input voltage amplitude influence the behavior of the capacitor output voltage by analyze the graph of its output voltage. And next, to examine how the variation of input voltage frequencies influence the behavior of the capacitor's output voltage by analyze the graph of its output voltage. And lastly, to verify whether the given circuit functions as a low-pass filter.
In this part, I will explain the concept of Simulink programming design for analyzing the given electric circuit. First, we open the MATLAB Simulink programming mode by typing Simulink. By choosing blank mode, we can start to do our design. First, we open Simulink library browser and select SimCAD. Next, we select AC voltage source component from the electrical source. Then, we set phase shift to 90 degrees in the AC voltage source. Next, we select resistor, capacitor, and electrical reference component from the electrical element and connect all of the components properly. Then, we set the resistor to 4.7 kilo ohm and the capacitor to 47 nanofarad respectively. Next, we select two voltage sensor components in the electrical sensors. One of them was connected to the AC voltage source for measuring the input voltage of the circuit, and another one of them was connected to the capacitor for measuring the output voltage of the circuit. Then, we select solver configuration component to give the solver setting information for simulation. Overall, we select two PS simulation converter components and connect them to two voltage sensors to convert the input Simulink signal into a digital signal. After that, we select Simulink. We select two display components in sync and connect each two to PS Simulink converter blocks to display the voltage measurement for the input and output. Besides, we also select scope component to show the graph. Then we double-click the scope component to set the number of the input clock to 2. After that, we connect two PS Simulink converter blocks to the scope to display the graph for the input voltage and the output voltage. Then we select whole circuit and do an area to make it look nice. Last, we use the annotation to write the title and our group members. Finally, the design of MATLAB Simulink program that used to analyze the given circuit was complete. For the graph setting, first, we double-click the scope. In the configuration properties of the scope, we set the layout to two, one at the top and one at the bottom. Next, we click the display window to name the two graphs and label their y-axis. The graph at the top was input voltage versus time and its y-axis is labeled as input voltage VI. Then another graph at the bottom was output voltage versus time and its y-axis was labeled as output voltage V0. Then we change the axis color to white color in the style. Moreover, we set the line thickness to 1 for both graphs. So this is how the graph show.
Assalamualaikum warahmatullahi wabarakatuh. For this part, I will present to you about the result. In this result, we have two simulations, and each simulation we have three cases. For simulation 1, we will change the P amplitude, and simulation 2, we will change the frequency. So we go for simulation 1. For simulation 1, case 1, we will set the P amplitude for 10 volt, and the frequency for 50 Hz. Then we run this simulation. So input voltage we get 10 volt, but the output voltage we get 9.951 volt, and the graph we get like this. So we move to case 2. For case 2, we will set the P amplitude for 20 volt, but the frequency is the same for 50 Hz. Then we run the circuit. Now the input voltage become 20 volt, but the output voltage we get 19.9 volt, and the graph we get like this. Then we move to case 3. For case 3, we will set the P amplitude for 30 volt, but frequency is the same, 50 Hz, and we run the simulation. Now the input voltage we get 30 volt, while the output voltage we get 29.85 volt, and the graph we get like this. As you can see, the peak to peak voltage for the graph become higher since the peak amplitude for each case increase. So we move to simulation 2, which change the frequency. For case 1, we don't need to change because we set the peak amplitude for 30 volt and the frequency for 50 Hz. As you can see, the input voltage we get 30 volt and output voltage we get 29.85 volt, and the graph we get like this. And we move to case 2. For case 2, peak amplitude still the same, 30 volt, but frequency we set to 100 Hz. And we run the simulation. Now input voltage we get 30 volt and the output voltage we get 29.43 volt, and the graph we get like this. Then we move to case 3. For case 3, peak amplitude still same, 30 volt, but the frequency we set to 150 Hz. And then we run the circuit. Now the input voltage still same, 30 volt, but the output voltage decrease. We get 28.75 volt, and the graph we get like this. So that's all for me for the result part. Thank you. Now we move to another part, and in this part I will present to you about the discussion. Based on simulation 1, the simulation show that voltage drop occurs when there is an increase in load, causing more current to be drawn from the source. This phenomenon is due to the resistance of conductors and components in the electrical circuit. The higher the resistance, the greater the voltage drop, resulting in a slight voltage drop in output voltage. Based on simulation 2, when the frequency value is changed from 50 Hz to 150 Hz, the output voltage has slightly different values with their input voltage. This is due to the phenomenon of frequency-dependent impedance or reactance. At higher frequencies, capacitors have higher impedance, making the load more resistant to current flow. This increased resistance results in a drop in voltage across the load, reducing current flow and resulting in less voltage across the load. So in summary, the circuit given for this project is a simple RC low-pass filter circuit that passes low-frequency signals and blocks high-frequency signals. The capacitor acts as an open circuit at low frequencies, with the output voltage almost equal to the input voltage. As the frequency of the input signal increases, the capacitor behaves more like a short circuit, causing a decrease in the output voltage. So that's all for me for this part. Thank you.
So this is the conclusion for our report. Through the result in simulation 1, it can be concluded that when the input voltage is changed from 10 volt to 30 volt, there was a difference between the input and output voltage. As we can see from the graph here, when the input voltage is set at 10 volt, this is the graph that we have obtained, where when the amplitude of the input voltage was time is at 10 volt and the output voltage was time is almost to 10. So we cannot see the exact value for output voltage over here because the difference is very minimum with the input voltage. And next, when the input voltage is set at 20 volt, so this is the graph that we have obtained. This is input voltage versus time where the amplitude is 20, and this is output voltage versus time where the amplitude is very close to 20. And when the input voltage is set at 30 volt, this is the input voltage versus time where the amplitude is 30 volt and the amplitude for output voltage is almost very close to 30. And as we can see from the result simulation, when the input voltage is set at 10, the output voltage is not exactly 10, but it is very close to 10, which is 9.951. And when the input voltage is set at 20, the output voltage is 19.9. And when the input voltage is set at 30, the output voltage is 29.85. So as we can see from the difference between the output voltage and the input voltage is very, very close from these values. And back to our conclusion. The voltage drop across the capacitor is proportional to its charge and it is uncharged at the beginning, whereas the voltage across the resistor is proportional to the current and there is a current at the start. But charge starts to build up on the capacitor, so some voltage is dropped at the capacitor. So initially the capacitor voltage is initially 0, so the resistor voltage is equal to the supply voltage. And when it is charging, as the capacitor begins to charge, it develops a voltage, so the resistor voltage begins to fall, which in turn reduces the charging current, which in turn the capacitor to charge at a slower rate. So this continues until the capacitor is fully charged. So once the capacitor is fully charged, the current stops flowing, the voltage drop across the resistor is 0, and the voltage drop across the capacitor is equal to the supply voltage. Okay, so next, what the simulation 2, it can be seen that when the frequency is changed from 50 Hz to 150 Hz, there were difference in the input and output voltage as well. So as we can see from the circuit analysis, when the frequency is set at 50 Hz and the input voltage is set constant, which is 30 volt, this is how the graph look like. The voltage, input voltage will be 30 and the output voltage is not exactly 30 but it is close to 30, and this is how the graph will look like for the frequency of 50 hertz. And next is as for the frequency for 100 hertz, the graph is still the amplitude of the graph is still the same, which is 30, and this is close to 30, and this is how the graph will look like for the frequency of 100 hertz. If we compare the first case, this is for 50 hertz and this is for 100 hertz. The 100 hertz graph is much more compact and very close to each other because we increase the frequency from 50 hertz to 100. And next is for 150 hertz. This is how the graph look like. The input voltage is still the same, 30 volt, and the output voltage is close to 30. We can see the difference over here. This is exactly at 30 and this is not close to 30. It is getting close to 30, and this is how the graph look like, very close and compact because we increase the frequency to 150 hertz. Okay, and from the result simulation table over here, we can see the input voltage is constant, 30, 30, 30, and the output voltage will be different, which is 29.85 for frequency of 50 hertz, and 29.43 for frequency of 100 hertz, and 28.75 for the frequency of 150 hertz. And these are the difference for the three cases. So going back to conclusion, this is due the output voltage is different with the input voltage because this is due to increase of frequency will also increase the circuit reactance, which when combined with resistance will increase the voltage drop. So the high frequency will also increase the effect of magnetic material on cable reactance and heating, and at the same time as the frequency increases, the capacitor voltage lags behind the signal by 90 degrees, while the resistor voltage becomes in phase with the signal. And last but not least, moreover, the simulation has proved that the given electric circuit is a low-pass filter circuit. Low-pass filter means that it will block the high-frequency signal and it will only allow low-frequency signal. Since the results from the program are same with the theory, the design program is considered successful. Therefore, all the objectives of this project have been achieved. That's all from me. Thank you.